So we wanted to keep this relatively informal and do a bunch of demos and talk through things with you. So if you have questions, do interrupt at any time. I guess Zoom and these kinds of online meetings are new to all of us. We'll try our best. Okay. Right. So as I mentioned, this part of this presentation is in the context of a project called Project Everest. It's a joint project between Microsoft Research and several other institutions, including INRIA, Carnegie Mellon, the MSR INRIA Joint Center in Paris, and others, folks from the University of Edinburgh and the University of Rosario in Argentina, and several other institutions where we, for instance, had many interns from many different places. So that's the Project Everest website. But one of the things that we're interested in is in building high assurance implementations of internet standards that implement various communication protocols, secure communication protocols, notably things like TLS, QUIC, and the cryptography that underlies them, things like RSA or SHA, elliptic curve crypto. The way in which we're going about trying to build these components is to program and verify them in a tool called FSTAR, which is a programming language that we've been designing and implementing at MSR for a few years now. What FSTAR is broadly speaking, it's a programming language and a proof assistant based on dependent types. And it has a few notable features. So let me just start with sort of a high-level tour of what FSTAR is before we dive into more specific uses of it. So it's a functional programming language with effects. So it's at some level, as a programming language, it looks like OCaml or F# or Haskell. It's a language in the ML family. And is extracted. You program code in FSTAR, and you can extract, after having verified your program, you can extract it to OCaml or F# by default. But a subset of FSTAR also compiles to C code, and we're going to look at a bit of that today. And we have several other subsets too. We have embedded DSLs in FSTAR for programming assembly language, and there's a backend that extracts to WebAssembly and so on. Beyond being a programming language like mainstream ones like OCaml or Haskell, it's one of its most distinctive feature is that it's also a verification system, and it's got SMT-based verification sort of built into the type checker, making it look a bit like other SMT-based verification languages like Daphne or Y3, if you're familiar with those. On the other hand, rather than being based only on a first-order logic like, say, Daphne, FSTAR's core type system is built on dependent type theory, where the type theory that underlies FSTAR should be familiar to you if you come from a background with in languages like Coq or Lean or Agda, where it's full dependent types probably it's actually closer in some sense to GNU Perl than the languages that I've mentioned, since the flavor of dependent types that we use has a kind of extensional feeling, flavor, more like GNU Perl rather than, say, Coq. It also has a meta-programming system where the FSTAR is its own meta-programming language, and we use FSTAR to, in this mode, both to meta-program other FSTAR programs, as well as to write proof automation using tactics. Again, similar to several other proof assistants out there. We've been using FStar in Project Everest for some years now, and various components that we build are deployed in the wild. Within Microsoft, we have uses of Everest and FStar code in several places. Recently, we've been working with Windows and Hyper-V, which is the main isolation technology used in Microsoft Azure, to replace some of their code that does network message parsing with verified code produced from FStar. Verified Merkle trees in FStar are part of Azure Confidential Computing, one of a blockchain used in that technology. We provide an implementation of QUIC, a new internet communication protocol, as the TLS components of QUIC to a Microsoft implementation of QUIC called MS QUIC, and several others. Notably, we have verified cryptography in many places, including Firefox, the Linux kernel, Embed TLS, and so on. Code and proofs produced by FStar runs in a large number of places right now. I mean, by some metric, nearly every message processed by, say, Microsoft Azure will go through a piece of code verified in FStar. This is, we're pretty happy about this. In a way, it's, I think, the kind of proof technology being developed in the SIGPlan community is seeing its way into mainstream software in many dimensions. So we're going to talk today mainly about how we do secure communication components, and I want to focus on sort of three main ingredients that we think go into these components. There's cryptography, which is we see it as being programmed in C and assembly code, low-level crypto that's very performance sensitive. Then there's a set of components that deal with message handling, things like parsing and formatting network packets before sending them out on the network or receiving them from the network. And then there's some protocol-specific logic that typically involves a state machine, some concurrency and distribution that sort of orchestrates a distributed program, or like the core state machine of TLS that's implementing the TLS handshake. So these three classes of components all have sort of diverse requirements, and we want to build these components in a way that we can compose their proofs in a single framework and provide a single coherent theorem about a system that we build using these components. And the way we do that is to embed in a single proof assistant in FStar various DSLs that enable us to program, say, both cryptography and message handling, and then compose their theorems to get a single theorem about the code that we extract. So in the case of crypto, one of the libraries we produce is called Evercrypt. It's a comprehensive cryptographic provider that's providing many crypto algorithms and constructions. Jonathan is going to tell us about Evercrypt and demo a generic library for big number arithmetic. For message handling, we have a library called EverParse, which is a library of verified low-level parser combinators. And Tahina is going to give us a demo about a short talk and a demo about using EverParse to parse employee records. For the protocol logic, we've been working on this is quite fresh, a new embedding of a concurrent separation logic in FStar in a system called Steal. And Aymeric is going to show us a bit about Steal, including how we encode session types for protocols and a semantics for concurrent separation logic in FStar. for steal. So a quick taste of F-star. At some level, it looks like the syntax looks like OCaml, but with types that are richer. So here is a classic recursive function over an inductive data type describing a length indexed vector. I'm going to go pretty quickly, so do interrupt me if you have questions. F-star is inherently higher order, like other functional languages in this tradition. So things like maps and folds over these inductive types are quite natural to write. The distinctive thing, though, in comparison to things like to other systems like Coq, is that F-star has effects that are user extensible and definable within F-star's type theory. So you can write stateful programs like, say, increment, and that's going to increment a reference to mutable state, to mutable, a reference to an integer, and you can give it a specification in F-star that tells you, in this case, for instance, if you run increment in an initial state H0 that contains the reference R, then increment ends in a final state H1, where the value of R in H1 is 1 greater than its value in the initial state. And you can do this with many effects and combine them. So for instance, here's a piece of code that reads an integer from input, checks if it's 0, it raises an exception. Otherwise, it does division with that with the integer that it read from input. And you can give this a specification that describes all of these effects together in a way that you choose to model. So how am I doing on time? I just wanted to quickly show you a demo of a very simple F-star program to give you a sense of how the tool works. So here is memcopy programmed in F-star. It's this is a tail recursive memcopy that's trying to copy bytes from the source buffer to the destination buffer. And a buffer in this case is an array of bytes indexed by a length. And here, if you give it a spec in F-star that requires, in this case, for instance, that that the source and the destination buffer have to both be live in the initial state, that they have to be disjoint, and that if you start in an initial state H where the source and destination buffer agree on their contents up to the current index, then you end in a final state where they agree on their contents all the way up to the end of their, up to the entire length of the arrays. And what this code does is only modifies the destination buffer. So if, for instance, you were to not include one of these preconditions and try to verify this code, F-star would complain here saying, here at the source buffer, when you're doing an indexing of a buffer, you need to prove that the buffer is live before you index it. And that's a kind of enforcement of spatial memory safety. If, for instance, you did not include the fact that these two buffers were disjoint and you tried to verify it, here F-star would tell you that it could not prove this inductive invariant on the recursive call, since the prior write may have disturbed potentially some of the contents of the source buffer. So that hopefully gives you a very quick flavor of the way in which you write and interact with F-star programs. Once you've verified a program like this, this particular program is in a subset of F-star that extracts to C. So you can, right, so if you run, there's a tool that we have that extracts F-star to C programs called Kremlin. If you feed this program to Kremlin, it will extract this memcopy to a C function that essentially erases all the specifications and produces C code that is hopefully recognizable as a tail recursive memcopy. You can also instruct Kremlin to run in with a mode that does tail call elimination, and it will produce a while loop instead. Or you can use F-star libraries that encode loops in the source language and program directly with a looping combinator in F-star. Or in the limit, you can also write this mem copy in assembly and link it to your C program, in verified assembly embedded in F-star, and link it to your C program. So there's a kind of a diversity of options available. So I'll stop there and hand over to Jonathan, who's going to tell us a bit more about the kind of crypto code that we build.
Sure. There's some questions in the chat, so maybe you can take over on the questions while I present.
Yep.
Okay. So it says you cannot start screen share while the other participant is sharing, so you may have to stop.
I stopped.
Okay. Is my screen visible?
Yes.
Okay. So essentially what I wanted to do in my allotted time was give you a brief overview of one, how we do cryptographic proofs and what is the approach that we generally use throughout our cryptographic library, Evercrypt, and do a brief code generation demo and show you a little bit how we leverage metaprogramming to get as much C code as we can while minimizing the verification effort. So I just have a few slides. These are very generic, but they essentially give you the essence of what we do. We always start by authoring our mathematical specifications in F-star in a very concise, readable subset of F-star just to embody what it is that we are aiming to verify. So this slide is using GF128 as an example, which is a polynomial field. And you can see that the definition of the polynomial field fits in essentially less than 10 lines of code. This stuff is meant to be readable, auditable, and that's really our source of truth. So this should be the only thing you have to read if you want to convince yourself that our cryptographic library is doing the right thing. Because it's so important, we're actually pretty cautious about our specifications, and these specifications are not in low-star. They don't extract to C, they're in pure F-star. They're written with lists, sequences, mathematical integers for maximal conciseness. So what we do to make sure that we didn't get anything wrong is we extract those specifications to OCaml using the general extraction pipeline of F-star, which Nick mentioned earlier. And this means that we can run our specifications on hundreds and thousands of test vectors. Once we're happy with our specifications, we do a second specification that is still pure F-star, but this time that is a lot more precise and a lot more concrete about how we're going to do things. And this we call pseudocode, implementation blueprint, or functional implementation of our algorithms. So on the right, this is an example of the exact same specification, but this time introducing things such as choices of representation, loops to iterate and to actually compute the field multiplication instead of saying, let's just do it using mathematical integers. And there's a first step of proof equivalence that states that the functional implementation is a refinement of the high-level specification. Once we have this functional implementation, we now have two choices in Evercrypt, our cryptographic library, to implement that functional implementation. Our first option is to implement it using a tool called Veil, which comes with its own dedicated syntax, and that is essentially a deep embedding of assembly language into F-star. And that allows you to drop into assembly to write, say, the inner core loop with all of the hand-tuned unrolling or the hand-tuned vectorization that will give you the exact maximum performance that you expect from a cryptographic algorithm. From the dedicated front-end syntax of Veil, the deep embedding in assembly is generated, and then a proof runs to show that the semantics, once run over the sequence of assembly instructions, refine the functional implementation. Our other option, if we want to implement that, is to use low-star, which Nick mentioned earlier, and the subset of our cryptographic code that is written in low-star we refer to as Hackle-star, which you may have heard about. And Hackle-star is written in that shallow embedding of F-star that resembles C, that has a C-like memory model, that has C-like loop combinators and many other facilities. And low-star pretty much looks like this. Still looks like stateful F-star code, except that you have a few special combinators like copy or like sub. Copy generates a call to memcopy in C. sub generates a pointer addition in C, and you can see those special effects. For instance, the stack effect indicates that this piece of code does not perform any heap allocation and is strictly using temporaries on the stack. And so we write a fair amount of code in that setting. We extract either the vel code to assembly, or as you can see on the right, to just a bare sequence of assembly instructions. We extract the low-star code to the C code via the Kremlin compiler. We have a model for what it means for the two of them to interoperate together, and they get combined into that big cryptographic library, which we call Evercrypt, which is the crypto for Everest. A quick word about what exactly it is that we verify in Evercrypt. We verify safety, so that's temporal and spatial safety per RC memory model. That means that you don't write outside of an array's bounds, and you don't use an array after it's been freed. We have, of course, functional correctness. That's what I was talking about earlier. And we have a built-in discipline of treating input data as secret, which prevents the most egregious kind of side channel attacks. Essentially, by using an abstract type, you are prevented from doing divisions, using your secrets for accessing arrays, or using your secrets for branching because your secrets just aren't Booleans. And that is pretty much the essence of the Evercrypt cryptographic library that we are developing as part of Everest. I would like to show you a little bit of code. I think it's more fun if I do an interactive demo and jump a little bit into the code. So I probably should increase the font size a little bit. So this is a line count that I ran in the HackleStar repository, just to give you a little bit of an order of magnitude. So this is the generated C code and H files. So that's with white space and with comments. But this is 50,000 lines of generated C code. And for the assembly, we have 15,000 lines of generated assembly. So this is pretty much the order of magnitude of the library that we distribute. And we have a fairly comprehensive set of algorithms. We have big number arithmetic, several variants of Blake 2. We have 4 variants of Cha-Cha-20, depending on your processor support for vectorization. We have Curve 25519, 2 different versions. We have ECDSA, ED25519, Frodo, several variants of HKDF, HMAC. We have many variants of a new box-like API called HPKE. We have a variety of hash algorithms, SHA-1, SHA-2, etc., SHA-3. We have the box API, Poly1305, RSA-PSS, and many more APIs. So we are getting close to the point where we are a reasonable choice if you just want to get fresh, verified cryptography in your existing software projects. And the really good thing is it's C and assembly, so anyone can use that. A little bit of a word about the source F-star files. So I ran a line count in the HackleStar directory that combines all of the cryptography for Everest, HackleStar, Veil, and Evercrypt. And so the Veil part, which is the assembly DSL part, is about 24,000 lines of source plus a few more thousands in terms of side specs and auxiliary stuff. The low-star code that we were talking about is about 65,000 lines of code. So you can see that the proof-to-code ratio is actually not that bad. We have, all in all, maybe a little under 200,000 lines of handwritten source files. So I would say that this is about a 3-to-1 code-to-proof ratio. And that's essentially the order of magnitude of our cryptography in Everest. So one last thing that I would like to show you is do a little bit of a code jump and show you how something I did actually fairly recently and that I think might be of interest. So generally, one thing that we do in our cryptographic verification is that we are very lazy. We try to minimize our verification effort and try to get as much C code as we can out of it. It's important for productivity, for maintenance, and for generally having a good experience writing cryptographic code. And one way to achieve that is to use metaprogramming as much as we can. And we have really, over the past year, doubled down on metaprogramming as a way to significantly lower or proof to code ratio. So this is a relatively self-contained example that talks about big nums, and I'm just going to cover the kind of specialization we do. Big nums are essentially a series of 64-bit integers, which we call limbs. And if you have a 4096-bit big num, you just need 64-bit integers to get that many bits.
Sorry, could you make it a little bit larger?
Yes, no problem.
Thanks.
Is this better?
Yep, thanks.
Okay. So essentially, when you write your big num library, you want your big num library to be generic on the size of your big nums. You want it to take any size of big nums, including at runtime, because you may not know what size of big num the user is intending to deal with. However, sometimes you just know that you want 4096 big nums, and for that, you would like a specialized version of the code so that you see all of the code specialized for 64 limbs, which will mean that all of your loops have constant indices and that they can be nicely specialized and vectorized by the C compiler. So what we do is that we essentially say that this combinator, the addition is a loop, okay? It's just a fill elms loop that essentially performs an addition for each limb and propagates the carry C all over from one loop iteration to the next. And so essentially what we do is that we do partial evaluation. We do our addition. We define our 4096-bit addition to be the specialization, the partial evaluation of the generic function applied to a constant size where n is equal to 64 for its first argument. We do the same for a variety of base operations. And what this gives us is C code that is wholly specialized for that flavor of big nums. And for instance, you can see here that the upper loop index is specialized to be 64 because we have 64-bit limbs in our 4096 representation. And that's the C code that comes out of it. It may seem silly, but the nice thing is you can actually apply that pattern all the way. So next, we define a generic library of big nums, and we define a type class of big num operations. And that means that you can write upper layers of the big num scaffolding, such as a Montgomery reduction on top of a big num type class, which contains specialized instances of all of the operations that you need for a given big num representation. And that means that if I jump back to the C code on the right, you get C code that is specialized for the instance of your type class, and that you get, say, a Montgomery reduction that is calling specialized versions of all the functions that you defined earlier, therefore giving you C code that is not only readable, but also that doesn't have any runtime genericity on the size of your big num. And so we apply that methodology on many, many layers. There's a type class of Montgomery operations for big nums, and then we can define with all of these type classes the modular exponentiation that is at the bottom of this file. Let me show it here. Yep, right here. And that calls specialized functions such as precomp or to and from or mod x loop that have been wholly specialized for a given big num representation. And now we get the best of both worlds. We have a generic library of big nums that can take the length at runtime, but we also have a wholly specialized version of it that contains no runtime genericity. And that is the sort of the essence of the metaprogramming that we do in Evercrypt. We have many more techniques for metaprogramming. We're using it with tactics that rewrite your call graphs automatically, with functors that allow you to encode a generic construction on top of a block-based algorithm. And we really have many interesting flavors of genericity in Evercrypt. I think I only went overboard by 3 minutes, so I'm going to stop sharing and let Tehina tell you a little bit about a wholly different class of verified applications, which is verified parsing.
Thank you, Jonathan. Let me share my screen. Alors, here is it. Share. Okay, so thank you, Jonathan and Nick. And now I am taking over for Everparse, which is a very automatic generator for verified efficient parsers for data exchange formats. So many people claim that parser research is done and so 1980s, but such infamous bugs, as cloud bleed are actually parsing bugs, in the sense that a buggy parser can lead to leaks of secret and sensitive data. And so that's one class of bugs among many others that we would like to guard against by implementing verified parsers and serializers. And that's what Everparse is for. So we want to generate verified C parsers and serializers for data exchange formats, so networking or host-guest communications in virtual machines or anything. So TLS, Bitcoin, ASN1 certificate signatures or anything. We want to generate zero copy C implementations. That is, instead of reading and copying data from the byte representation to a high-level representation, we would like to access the data directly from the byte representation as needed. And for serialization, we want to minimize and track the allocation of intermediate objects. And we want to generate a verified code that is verified with respect to memory safety. That is, no buffer overruns, no buffer, write after free or anything like that. Functional correctness, the fact that serialization and parsing are inverse of each other. And we also have some cases in TLS, for instance, where we need stronger security properties such as injectivity to avoid malleability attacks. So we have a paper published at Usenix last year. We already have ongoing and completed applications such as the verified validator deployed for Azure, networking communication, and host-guest communication between the host and the guest. And we are currently working on Quick and TLS. So here is an example of data format description that we are actually dealing with TLS. So this below is a data format description that you find verbatim in the TLS specification, in the TLS standard, the RFC 8446. It describes the data, it describes the format of the client hello message when the client tells the server which cipher suits and which cryptographic algorithms the client supports, to ask the server to pick one of those. And so the message starts with a version number, random bytes, and the session identifier, and so on. And above here you have some representation of valid data with respect to this data format. So 2 fixed bytes for the legacy version, 32 bytes for the random seed, and a variable length session ID starting with prefixed with its length in bytes, and similarly for the cipher suits, which is a list prefixed with its length in bytes instead of number of elements. So voilà, that's what we are dealing with Everparse. And so from such a data format description, we automatically generate validators which take input buffers and check whether they contain valid data with respect to the data format. Accessors to access valid data within the input buffer directly, and formatters to formatters to serialize data with respect to this data format. And so this process is automatic. That is, from the data format description, we automatically generate validators, accessors, formatters, and so on, and we automatically prove them correct. So under the hood, we actually generate F-star code in particular under the form of low star code. So this subset of F-star that is extracted to C that Nick and Jonathan just showed you a few minutes ago. And we link with the low parse library, which is a verified combinator library for parsing and serialization. And then we use Kremlin to extract this code to verify the C code. So let's take a simpler example for the rest of my slice of presentation. So I want to parse an employee record, each employee being represented by its name and its salary. So the name is a variable length byte sequence prefixed with its length in bytes. So my name is Tahina and it takes 6 bytes. So it starts with 6 and each character of my name, and then followed by the salary encoded in 2 bytes. So what we generate a high-level F-star data type for specification purposes. We generate a parser and serializer specifications in F-star. We generate functional implementations, inefficient implementations that are targeted to OCaml extraction, just for testing purposes. And we generate a low star and C low-level implementations, validators that check input correctness without making any copies, accessors to access fields of structs or payload of a tagged union or anything without any allocation, and validity lemmas and finalizers to for incremental serialization to allow the user to have their own strategy for memory allocation. So for the employee example, so here I am going to show yes. So yes, here is the data format description, and from there I automatically generate the F-star code so it's currently generating. So I can show you. I generate the parser and serializer specifications. The parser takes input bytes and returns none if parser fails, and sum high-level data and the number of bytes consumed if it succeeds. And this parser has special properties that we automatically prove. Injectivity for malleability, consumption bounds, whether it has such properties as a strong previous property, the fact that the parser succeeds, if a parser succeeds, then it will always succeed independently of the data that follows what you parsed. And this is all controlled by metadata, which I'm shortly presenting. And the serializer has to be inverse of the parser. It takes a high-level value and returns a sequence of bytes, such as so that it's that sequence of bytes is parsed back to the high-level value. And so now it's done, yes. And so I can show you what we are actually producing. We are producing a high-level type employee with the name and the salary. We are providing metadata for the parser that explains how many bytes the parser consumes, at least 4 and at most 258. A parser specification, a serializer specification that is proven automatically correct with respect to the parser. Functional implementations of the parser and the serializer and the size, the validator that takes an input buffer, a jumper that takes an input buffer and jumps beyond the valid representation of data for with respect to this data format. Accessors that, given an input buffer, give you access to the fields of, given a valid input buffer, give you access to the fields of the employee record, and lemmas for serialization, telling you that if you have a valid name and a valid U16 integer, then you have a valid employee record. And so how are we proceeding? We are proceeding by generating combinators. Sorry, assembling combinators. We specify parser and serializer combinators in pure F star as part of the low parser library. On those combinators, we prove injectivity and inverse properties. And then we implement those combinators in pure or effectful low star for the validator, the jumper, and so on which we prove functional correctness and memory safety. And then we generate parser serializer specifications by assembling such combinators so that there are no manual proofs required. And everything is proven correct by virtue of typing. So it's correct by construction. And then we extract to C using Kremlin. So more concretely, yes. We have a combinator for pairs that take two higher order combinators for pairs that take two parser specifications as arguments, one for each component of the pair. So an employee is parsed from the parser for its name and the parser for unit 16. And then once we have a pair, we can rewrite this pair into a record value. And that's the rewrite combinator that we have in low parse. And that's what we are actually generating for the employee record, for the specification. Yes, well, the parser for the pair takes the parsers for the two components of the pair and generates a parser for the pair. And the parser for rewrite takes the parser for the data before rewriting and the function to rewrite, and then it generates a parser for the rewritten data. The validator implementations follows the same pattern. That is, we also have combinators for validation. And then thanks to inlining and many other meta programming and code transformations from low star to C, thanks to Kremlin, we these transformations from low star to C through different languages, intermediate languages that you can find in the ICFP 2017 paper, verified embedded low-level programming in with low star. And that's the code, the C code that we obtain by extracting those validator implementations to C. It's efficiency code in the sense that it curls the validators for the name field, and then it checks whether it has enough remaining space for the salary as 2 bytes, and then it returns the position one past the end of the input data, the input buffer that has been validated. One past the end of the data that has been parsed with respect to the employee parser specification. And so you can see that the validator for unit 16 is inlined, and the combinators are inlined as well. And that's how it works. And then from sample code that use these validators and accessors written in low star, so it takes I validate an input buffer, and if it does not validate, then I return 0. Otherwise, I access the salary and I read it, and it's extracted to C into a readable C code. As you can see here, I code the validator, it fails, then I return 0. Access the salary, it returns me a position where the salary is, and then I read the salary value from that position. We support pairs, lists, refinements, tagged unions, integers, enums, fixed length, bytes, variable length bytes, and also bit fields, bit tagged unions. These are necessary for TLS, Quick, and other implementations and applications, and we generate validators that are significantly faster than the reference implementations. For Bitcoin, for instance, we generate 13 times faster implementation than Bitcoin Core. And voilà, that's all I have. And that's also what I want to mention is that it's a sweet spot for verification, in the sense that you can write your data from a description, and you just push a button, and you have no verification effort to do by yourself. Everything is done automatically, from verification to code extraction. Voilà. Thank you. And from now, I can, I can leave the rest of the presentation to Emeric for steel and concurrency and other aspects in Everest.
Thank you, David. Let me share my screen. Okay, do you all see my screen now? Good. So as Tahina mentioned, I'm going to talk a bit about how to do protocol verification in FSTAR, and especially in STEEL, our most recent work on providing a concurrent separation logic framework for FSTAR. And so to demonstrate this, I'll mostly look at it from the client's perspective. And so in STEEL, we provide two libraries, steel.channel.protocol, which allows you to specify protocols, and steel.channel.duplex, which allows you to implement protocols. And so my example here is going to be a fairly simple ping-pong protocol where a client sends an integer and receives an integer that is strictly greater. So the first step is to specify this protocol in FSTAR. And so it's here, this ping-pong that's implemented here. So this is pretty straightforward. The idea is, as I was saying, you are sending an integer and you are receiving another integer, which has the additional property, this refinement here, but it is strictly greater than the one you sent. And so after sending the integer, receiving an integer, you are done, the protocol is over. So how would you implement this in FSTAR? Well, the first part is implementing the client side. So a client is going to take as an argument a channel, and this channel is going to be indexed by the protocol it satisfies. So in this case, the ping-pong protocol. And this implementation is going to have this steal effect, which allows you to give a pre and post condition in terms of separation logic assertions. So here, my precondition is going to be that I own the separation logic assertion corresponding to an endpoint associated to channel C. And the last argument of endpoint is what are the next steps, what are the remaining steps in the protocol for this specific endpoint. So initially, for the client, I haven't started yet executing the protocol, so I have an endpoint for the full protocol. And after execution of the client, my post condition here is that I have the separation logic assertion that says I still have ownership of this endpoint, but I'm done with the protocol. There is no action left that remains to be done. Hence, I have here this protocol.done. So in the implementation, how does this work? Well, we have this client that takes the channel. And our first step, according to the protocol, is to send an integer, any integer. So we're going to arbitrarily choose to send integer 17. And this is done using the send capabilities that are given by the generic duplex library. And after that, we are now receiving an integer according to the protocol. And so, oops. And so after receiving the integer, the protocol tells us that, well, this integer is actually greater than the one we sent. And so in this context, that means that y, the integer we received, is greater than 17. And that's a fact that is available in our context and that can therefore be accepted. And so finally, we conclude by returning unit to end the protocol. And so we have a fairly similar implementation for a server side. So again, we take as an argument a channel corresponding to a ping-pong protocol. And in this case, our precondition is that we have an endpoint where the remaining steps are the dual of the ping-pong protocol. And so dual is, again, a generic utility for specifying protocols, which allows you, if you specify the protocol on the client side, to see it from the server side. So basically what it does is it flips all of these sends and receives, it swaps them. And so again, after executing the server side, we still have ownership of our endpoint, but we are done with the protocol, there are no steps remaining. And so very similarly to the client implementation, the server implementation is again using the duplex facilities to first receive an integer, and according to the protocol, it has to send one which is strictly greater. So again, we arbitrarily choose to just increase this integer by 42 and conclude with the protocol. And so what's interesting here is that all of this, the fact that the protocol is satisfied, is followed, is ensured by typing. So for instance, in this example, I have a wrong server implementation where you can see here, what I'm trying to do is send an integer, which is actually smaller than the one I received. So I'm not satisfying the protocol. And here it's perhaps a bit small, but f star, when I'm trying to type check this, is pointing me specifically to these arguments and telling me that, well, it was expecting a message that was satisfying the protocol, but instead it just got an integer. So it's not able to prove the refinement that was specified in the protocol in this case. And so if I don't have, I mean, I just cannot type check this without this expect failure annotation, which allows me to specify that something is wrong with this program. So now that I have a client and a server implementation, I can initialize both sides using this newchan generic primitive from, again, the duplex library. So newchan is a primitive that takes a protocol and creates a channel C that corresponds to a protocol. And it also adds two separation logic assertions in the context, which corresponds to the protocol itself and its dual. So basically, it gives you ownership of endpoints for both the client and the server side. And so when I have this separation logic assertions, I can use the standard par combinator from concurrent separation logic to execute the client and the server implementation in parallel. And this is doable because these two endpoints are separated resources. They are starred according to the separation logic star. So I can safely execute them in parallel. And lastly, to ensure that here, this client server has a trivial pre and post condition emp, meaning I don't have any ownership of anything. I am just dropping the remaining endpoints because our separation logics are fine. And so here, these type checks as well. So now that I have this, I can actually execute a multitude of such instances in parallel. And so I have this function many, which is going to use a generic fork join library that we implemented to spawn n instances of this client server. So how does this work? So here, let's look at the recursive case first. The important part is this fork command. So fork here is going to spawn a thread and execute our client server implementation, which executes the client and server in parallel. And the continuation is going to recursively call many again to spawn the n-1 threads. And importantly, it's going to record the list of the threads that have been spawned to call this client server. And so finally, once we have spawned all the threads, we are going to use this join all utility that we implemented just above, that uses the join part of our generic fork join library. And so that means we are just going to wait for all threads to terminate before finally returning unit and concluding. And so that's what gives us, from a client's perspective, the capability of implementing and verifying a protocol and doing this in a concurrent way. But so how does this work in practice? Like, how is it justified to do this concurrency? Well, as part of our ongoing work, we have a model, a semantics of concurrency. And the way it works is we are working on atomic actions. So an actions is just some modification of a state which has a pre and post condition, where we assume that we are framing. And we have computation trees that operate on these actions and that allow you to compose these actions in parallel. And so here the important parts are, if you look at par, it takes two actions, M0, it takes two computation trees, M0 and M1. And if you look at actions, the actions themselves contain their continuation, which is a divergent function. And so what we're going to do is, based on these computation trees, we're going to provide an interpreter. And so, for instance, the first part of the interpreter is the step function, which performs one step of the interpreter. And so the way we're going to handle concurrency is we're going to assume a source of randomness as a stream of Booleans. And according to this stream of Booleans, we're going to step either on the left side or on the right side when stepping a par node. And so that means that since we have this source of randomness, we're going to have to consider all possible interleavings of actions and all possible interleavings in our execution of a program. And so at the very end, we have this entry point for our interpreter, which is this run function, which has as a precondition that the precondition we specified on the state is satisfied. And that ensures that according to our interpreter, so for any interleaving, the post condition that we specified is satisfied. And so that's what gives us a way to specify a concurrency and to use concurrency in Steel. So as Nick was mentioning at the very, very beginning, Steel is still a work in progress. So we have a paper that was accepted at ICFP recently that gives more details about this semantics. Like this version that I presented here is a simplified version of the semantics. So it's giving more details about the semantics. It's also showing some more examples. But Steel as a framework, so for clients to use, is still a work in progress. And among other things, what we're working on right now is how to make it a usable framework. How do you automate framing, which is at the core of separation logic? How do you ensure that you have extraction to low-level C, for instance? And how do you ensure that you have all the libraries that you might want to use in an actual framework? Thank you.
Wow, we finished at exactly at the end of the hour. I thought we might run a bit long. You have some time for questions? I see there's been, we've enjoyed the chat, the text chat, but if there are other questions people have, we have some time for it.
I've got a question. Or is,
Yep.
what's the status of the WebAssembly backend that you had for a while?
Jonathan?
Answer that one. So Lowstar compiles generally to C or to WebAssembly. The WebAssembly backend for Lowstar is complete, and we are distributing all of the Lowstar parts of our cryptography compiled as WebAssembly. We just recently had very nice idiomatic JavaScript bindings on top of the generated WebAssembly, meaning that you can now call your code with native array buffers from JS.
That's cool.
I need to write a blog post about it to let the world know.
And can you use it from Rust as well if you're compiling Rust to WebAssembly, or is that harder?
We have not tried that.
Okay.
It's a good question. The Rust interrupt comes up often. What our plans on that front are to have a library of official bindings for Rust that might or might not be auto-generated, like we did for Camel. We now have also like OCaml bindings via C types with a really nice handwritten high-level API that uses functors to make it easier to call our crypto from OCaml. So we're hoping to do something similar for Rust.
Okay, thanks.
I have a question about F-star more generally. So at the beginning, when you showed the memcopy examples, it seemed that F-star works really hard to try to prove this implementation satisfying specification automatically. So if it doesn't happen, is there a possibility to prove something manually, like some hints for the type checker, or is there completely manual proof mode?
Yeah, yes to all of those, I guess. There's we first, our default mode is we typically first try to prove programs using the SMT solving backend of F-star. If that fails, then we tend to add calls to additional lemmas that help the SMT solver along. If you're trying to do something more advanced than that, then F-star has a tactic language where you can drop into it and do a proof manually. And often what we try to do is to define specific subsets, domain-specific languages, in which we know that proofs have a certain structure, and that allows us to define domain-specific automation for those subsets, either using tactics or SMT or a combination of the two.
That's neat, thanks.
Sure. All right, well, If there are no more questions, thank you to everyone. It's great to have this online community to share our work with, and thanks for all the nice questions.